Now we're going to talk about smooth and continuous graphs. So a smooth curve is a curve with no sharp corners. A continuous function is a function with a graph that has no breaks. The graph can be drawn without lifting the pen or pencil from the paper. So that's like, if you had a graph like this, and then it picked up over here. That's not continuous. But a graph like comes down to maybe do some stuff and goes up, that is continuous. And a smooth curve might look like that. And a sharp curve might become like that, and then does something like that. I'll say not smooth. Okay. Intercepts and turning points of polynomials. So this is kind of a big deal. This is based off of a couple different theorems, but the fundamental theorem of algebra. A polynomial of degree n will have at most n x-intercepts and n minus 1 turning points. So n x-intercepts, n minus 1 turning points. So looking at example 10, without graphing the function, determine the local behavior of the function by finding the maximum number of x-intercepts and turning points. So this has a degree of 10. The degree is 10. So maximum number of x-intercepts is going to be 10. It's actually going to be less than that. Just I can tell by looking at it, because immediately you could factor out that x cubed, and you'd have a negative 3x to the 7th plus 4x to the 4th minus x to the 1 plus 2. I don't think that's what they want us to do, though. I mean, so looking at that, obviously x equals 0 is an x-intercept of multiplicity 3. So you could say this has a most of 8 if you wanted to be technical there. But I think they just want us to look at this degree 10. And then if degree is 10, we have n minus 1 turning points maximum. So that'd be 10 minus 1 is 9. And there'd actually be less than that because of this x cubed. It is going to cross at the x-intercept, though, because that's an odd number. But I think I'm getting ahead of myself. 9 turning points maximum. Okay. Let's go on. What can we conclude about the polynomial represented by the graph shown in the graph based on the x-intercepts and turning points? So it's got 1 turning point, 2 turning points, 3 turning points. So it's going to be a quadratic, or a fourth power. So degree is 4. It only has 2 x-intercepts, but something's happening here. So the way I conclude on that one, the way I interpret this, it does have 2 real x-intercepts and 2 imaginary x-intercepts. So it's at least a 4. 2 x-intercepts that are real. And then 2 x-intercepts. Although I don't think they want us to go that way. X-intercepts that are imaginary. And since this is going out across the web, right, all of YouTube, I'm sure there'll be someone out there who's going to argue with me on that. But anyway, that's the way I look at it. When we see that kind of behavior where it's doing a rise and a fall again, but it doesn't cross the x-axis, that usually indicates an imaginary root. Or should I say complex? Okay, someone's going to argue that. That would be... I'm just going to say complex. Gosh, I want to say imaginary. having this little debate in my head right now, but okay, I'm just going to move on. I'm going to say not real, meaning they could be imaginary, purely imaginary, or complex that's not a non-real complex. Okay. Given this function, determine this last example, determine the local behavior. So we can just see we have 1, 2, 3 intercepts. So 3x intercepts. And it's going to be degree 3. If I multiply this negative 4x times x, it'd be a negative 4x cubed. So the other information, the maximum number of turns is going to be 3 minus 1, which is 2. 3 is the degree, minus 1 is 2, then minus 1. And I mean, I can go further and talk about the end behavior as well, but they didn't ask for that. But given that negative is going to be coming down like this, so it's crossing there. So this would be like 4 here. This is 0, obviously. And this would be like negative 3. So there's your graph, roughly. That's very rough. I mean, it's not, I'm not sure how high and low they're going to go. But I just threw something out there. Okay, and that's it for this section. Let's go forth and do the homework.